What I would like to present to you now is a very short introduction into my theoretical work that relates to the foundations of electromagnetism. And then I would like to show to you an experimental approach that uses water and quantum dot oscillations to create a charge separation with a goal to make a battery-like device that can be seen as a steady electron pump. Now, probably because I'm a self-taught researcher, I'm not too much tied to established ideas. I think it can be inspiring to create new theoretical approaches. My approach to the foundations of electromagnetism include a shift in perspective in relation to where energy comes from in the first place. Since I do not sympathize with the Maxwellian idea that, for example, a static electric field is a truly static phenomenon, I found the motivation to create a schematic model that sees a typical static field as something dynamic. If we look at the Maxwellian equations, energy is directly converted from one form to another, meaning what goes in at the front comes out at the back, and that's it. What is missing here is what happens in seemingly empty space-time between two source charges. How exactly is the observable energy from a first charge converted to a potential flow, and how is this potential flow again converted to an observable energy at a second charge? To get an idea of how this process could work, I used a concept coming from quantum electrodynamics theory, namely that the virtual particle is the carrier, transmitter, and creator of the electromagnetic interaction. Thereby, I assume that the virtual particle comes from space-time itself, making space-time the primary energy-carrying medium, and that the electromagnetic energy transferring entity is made up of a virtual particle alignment process proceeding at the speed of light. This alignment process works as follows. If we look at a virtual particle that appears next to an electron, then the positive side of the virtual particle is rotated towards the electron, and the negative side of the virtual particle will then be facing away from it. A neighboring virtual particle appearing next to a first virtual particle will be rotated in the same way, leading to an alignment process made up of locally appearing virtual particles. Thereby, I assume that the virtual particle does not move, but is attached to a frame. So all that moves is the alignment process itself. Once this alignment process arrives at another charge, this charge will feel a force, and then it can be accelerated by the locally appearing virtual particles. So the energy for the acceleration of a second charge comes from local space-time that is occupied by that second charge and not from the first radiating charge. This approach suggests that every charge is towards the energetic exchange with space-time an energetically open system. But at the same time, we know that energy is conserved, so it is clear that all electromagnetic systems behave like closed systems. This leads to following basic question. Why is observable energy conserved despite the fact that the potential flows are not conserved? This picture shows the so-called self-symmetrizing process. The self-symmetrizing process explains the cause for the conservation of energy. Now, if you could please visualize for a second an electromagnet there where it says input and a permanent magnet at the place where it says output. And in between the electromagnet and the permanent magnet, we have an air gap. That is the situation in an electric motor. Once energy is input into the coil of an ideal electric motor, this input energy is lost in an observable sense and is converted in the air gap into a potential form. then this potential flow, which I see as an alignment process of virtual particles, proceeds with the speed of light through space-time. As soon as this alignment process arrives at the permanent magnet on the other side of the air gap, these aligned virtual particles, or this asymmetrized space-time, creates a force on the permanent magnet. So the energy for the acceleration of the permanent magnet does not come from the electric input energy, but from that volume of space-time that is occupied by the permanent magnet. So why is it that the lost energy at the input, which is actually a violation of the conservation of energy in a negative sense, exactly matches the created energy at the output, which is again a violation of the conservation of energy, but in a positive sense? The reason for this is that the back-running magnetic field from the permanent magnet towards the electromagnet breaks the electrons in the coil, and that destroys the input dipolarity in the coil, leading to a decline of the magnetic field from the electromagnet. And since the forth and back-running magnetic fields from the electromagnet and permanent magnet are similar in intensity, we have an energy balance situation leading to the conservation of energy. So the conservation of energy is only existing at the end of an energy conversion process. This mechanism is, from my view, fundamental and may be transferred to the other interactions as well. Here is a comment from Prigogine that I'd like to read. According to relativity, events that are simultaneous but occurring at different locations to one observer may not be simultaneous to another. Hence, the simultaneous disappearance and appearance of energy as seen by one observer will not be simultaneous for all. For some observers, energy would have disappeared at one location first, and only some time later would it reappear at the other location, thus violating the law of conservation of energy during the time interval separating the two events. The reason why I am mentioning this is that I just want to demonstrate that it is possible to explain the reason for the conservation of energy in another way. What this means is that all particles in our world are quantum open systems, but they just behave like quantum closed systems. The next step for an energy conversion technology would be that we extract more energy from space-time, from the output, than we put in or lose at the input. How can this be achieved? It can be achieved by creating a new class of electromagnetic systems called asymmetric electromagnetic systems. An asymmetric electromagnetic system is a system that is not only a quantum open system, but it also behaves like a quantum open system. And how could that work? It could work by using a resonance that has a special characteristic. We need to create a resonance that has a non-self-symmetrizing quality. A non-self-symmetrizing resonance can be created by using two resonating systems that are brought into a double resonance. Each resonating system must include at least two charges or molecules resonating with each other and their own electromagnetic fields. Then the two resonating systems are brought into a double resonance. This double resonance must include a phase shift. This phase shift leads to the situation that more energy can be extracted from space-time during the collector cycle than is given back to space-time during the restoration cycle. Another phrase for a non-self-symmetrizing resonance that I use is coherent quantum fluctuations. Technically, this could be realized by creating a double resonance between two molecular systems made up of quantum dots and water. So what is needed is a self-sustained oscillation of water molecules and quantum dots resonating with their own electromagnetic fields. So what I'm showing here is the basic setup of the Reid cell and hypothesis. There's a nanocrystalline semiconductor material containing water clusters and quantum dots. The coherent water molecule oscillation in combination with spin oscillation of quantum dots energizes electrons. The integrated diode characteristic rectifies the tunneling current. The energy for the charge separation comes from external radiation, possibly also coherent quantum fluctuations. The hypothesis is the water molecules and quantum dots oscillate with their own electromagnetic fields, thereby extracting energy from the fields or virtual particles itself. Now, what we have here on the left side is, here this. The upper one, okay. The white field is a silicate material, the nanocrystalline semiconductor containing clusters and chains of water molecules, and they are attached to the aluminium, to the minus pole, chemically. So there's a chemical bond between the silicate and the aluminium. On the other side, we have copper, which is coated with silver and niob oxide. So the silicate has no chemical bond with the metal on that side. Now, I will get to that picture just now. I just want to point out a few general features of the cell. Now, the only possible electrochemical effect that is known to us is an aluminium air battery effect. The silicate mix is a solid material which has a pH of around 11. The ambient voltage is around 1.5 volts. The electrochemical effects are existing, but do not seem to be responsible for all current and energy. 1 gram of aluminium can deliver up to 2.9 amperage hours. The amount of aluminium corrosion is much smaller than expected in relation to the generated current. There is no visible corrosion at the plus pole. The silicate shows fluorescence, which is typical for quantum dots, low power output but constant. A 300-gram cell can generate approximately 3 milliamps at 1.3 volt, which is about 4 milliwatts at 25 degrees Celsius. The cells are since 1999 under permanent load with only little power decrease. A significant part of the current seems to come from oscillations that are generated in the silicate. There's a broadband radio signal on the voltage under a Faraday cage, and the best performance is at 37 degrees Celsius. I will get back to these measurements just now. The X-ray diffraction shows thermonatrite, which is rather a rare form of sodium carbonate, then differing sodium silicate, hydrates, silicate oxide, and an aluminosilicate structure that could not yet be identified. This whole thing is doped with a ferromagnetic isolator of manganese oxide. Now, there are two oscillatory phenomena playing a role in the silicate. One phenomenon is the self-sustaining dynamical nuclear polarization oscillation in quantum dots. The coupling of electron and nuclear spin dynamics is responsible for a wide variety of intriguing transport phenomena in semiconductor devices. The combination of these two effects, electron-nuclear spin exchange, which polarizes nuclear spins, and subsequent back-action on energy-dependent spin flip rates, gives rise to interesting nonlinear dynamical effects such as multistability, hysteresis, and intermittency. Perhaps the most striking phenomenon observed in double quantum dots is the appearance of spontaneous, stable current oscillations under the application of a static DC source drain bias. Now, what you see on the right are two quantum dots in blue, separated by a tunneling barrier in red. And if a static source drain bias is applied, you get these steady current oscillations. Another oscillatory effect playing a role in the cell is the self-adjusted sustaining oscillation of confined water chains in nanospaces here, for example, in a carbon nanotube. What you see here is a carbon nanotube and a chain of water molecules. And if that is the case, they most likely can move into a coherent oscillation. And this coherent oscillation lasts only for a very short time and runs into a chaotic oscillation again. And this moving in and out of coherence has a frequency of about 40 gigahertz. We show by molecular dynamics and first principle calculations that a water chain confined in carbon nanotubes can self-adjust into regular oscillation with remarkably lower entropy from random thermal motion with higher entropy at room temperature. The findings are expected to be helpful in creation of self-sustaining electromechanical systems driven by ambient energy. Now let's get a bit more in detail into the hypothesis and setup. Now, on the left-hand side, this light blue, what is in light blue here, is the silicate nanostructure containing water clusters, quantum dots, and a ferromagnetic oxide, creating a so-called diluted magnetic semiconductor as a spin injector. Now, this silicate is in direct contact with the aluminium, and when this semiconductor is in direct contact with the metal, the spin injection collapses, and you have spin up and spin down electrons moving equally well through. On the other side, we have a different situation. The silver is separated from the semiconductor by an isolator, which is the neob oxide. So we have a metal isolated semiconductor, which is a typical spin valve. So we have mainly a spin-up current moving in from the plus pole, and we have a differing resistance, of course, by spin-up and spin-down going out and by the spin-up current going in. Another issue is the pH gradient on the left side of the neob oxide and on the right side of the silver. I'm not going into that now in too much detail because it's a complex topic. The pH gradient in the porous neob oxide, as well as the electrochemical potential difference between the aluminium and silver, creates a DC source drain bias. This electric field, in combination with the coherent water oscillation, triggers a spin oscillation on quantum dots. Energy extraction from electron-nuclear spin oscillation, creating a tunneling current. The diode characteristic then rectifies the current. There seem to be three ways how to extract energy from an atom: fission, fusion, and electron-nuclear spin resonance coupling. Since the particles of an atom exist as a structural quality of the field and are made up of virtual particles, energy is extracted from the virtual particles in a non-self-symmetrizing way. That's why I had this long introduction to point that out. Now, this relates to the charge separation itself, but it still does not determine where the electrons are moving. The electrons have to be separated into a particular direction. That is done by the diode characteristic, which is created by a differing spin-polarized tunneling behavior at the aluminium with the chemical bond, that's on the left side here, and at the silicate neob oxide silver nanoparticles boundary. And this effect could be accompanied by a differing water structure-related behavior at the dissimilar surfaces. Now, if this hypothesis is supposed to be at work in the cell, this should be reflected in the measurement data. First of all, a picture from the silicate showing that it is made up of small spheres which have a diameter of about 1 micrometer, which corresponds to wavelength in the infrared. And I found this book in the 4th phase of water showing the protein encapsulated water made also of spheres of approximately 1 micrometer. Anyway, when you look at the small spheres here, that's, yeah, is that a coincidence? I don't know, maybe you can tell me. Okay, here we are looking at one aspect of the broadband radio signal that comes from the silicate. Up here we have the voltage of the cell being under load on a resistor, and here's the temperature in the room, going up and down a little bit, and as you can see very nicely, the voltage curve follows the temperature curve, which is showing the temperature dependence of the cell. And from the broadband radio signal, we took out a narrowband signal at 245 megahertz, and here we are showing only the amplitude of the signal, not the frequency. The lower line shows strong jumps in amplitude of an arbitrarily chosen frequency at 245 megahertz of up to 20 decibel when temperature and power output changes. The amplitude then stays on defined levels, indicating a relationship between oscillations and the generated current. The Reid cell is highly sensitive to temperature changes. At a higher temperature, we see a higher power output and vice versa. Now, to get a better understanding about the temperature situation, we made a high-precision calorimetric experiment, which is, from my view, very important, because if we make claims that we convert thermal energy into something or whatever, we actually need to investigate it by a calorimetric experiment to see what the energetic situation is. The orange line here shows a self-recharge phase of 4 hours, and here we have a discharge phase on a resistor. The blue line shows the temperature in the calorimeter, and we are measuring in a resolution of less than 1 millikelvin. This is 5 millikelvins from up here to here. This here is the temperature of the resistor, which is of course outside of the calorimeter, but this is not to scale here, it will be much higher. Now the self-recharge and discharge time is 4 hours each. The cell is temperature sensitive on one hand, but on the other hand does not convert the ambient temperature into electric energy. The expected cooling was 12 millikelvin per hour. There is no cooling under load or when putting it under load. The temperature just seems to act as a trigger signal, enabling the extraction from another source, possibly from coherent quantum fluctuations. Now, if you're looking at 12 millikelvin per hour, and this is a phase of 4 hours, we would expect a drop of 48 millikelvin. But as you can see, we have no change in temperature at all, and there's no heating likewise. So also from an electrochemical point of view, it's it's a strange result. Here we are analyzing the broadband radio signal. The gray line up here is the voltage line of the cell under load. Then we are zooming into the voltage signal, and the blue line shows only the peaks that go upwards, and the peaks that go downwards, they are filtered out. The red line shows the opposite. Here we only show the peaks that go downwards, and the peaks that go upwards are filtered out. And then we subtract one line from the other to receive the differential signal. And the differential signal gives you a statistical analysis, how many times per time interval is the cell in a self-recharge mode and in a discharge mode. And as you can see here, at 938 millivolts, that's exactly at that voltage, we see a resonance which lowers the power output a little bit. And at another voltage level, at 968 millivolts, we see an increase of the power output. So these two resonances, they are equally interesting because they show that resonance effects exist in the cell. Here we have another cell. We have a self-recharge phase of 7 minutes and a discharge phase under a resistor about 7 minutes. And the blue line here shows again the differential signal. And as you can see here, after 1 minute or 1.5 minutes, we have a much faster charging phase. And that is explained in such a way that the dipoles, well, after you have discharged the cell, the charge separation occurs everywhere in the silicate at the same time. And at the stage, the charges touch each other, and then it comes to a faster recharging phase. And then this, the higher the source drain bias gets, the higher the ambient voltage gets, the lower the frequency of this voltage oscillation becomes. And this is a feature that is known from quantum dots, that at a changing source drain bias, you have a changing frequency. Yeah. Here, this is the voltage curve of a cell after it has been put under a dead short. You can dead short the cells as long as you like. The longest dead short lasted for 4 years. It doesn't make a difference on the function of the cell. Anyway, when you open now the dead short after a while, the cell recharges on its own, and then it overshoots the ambient voltage by a few millivolt. It's even up to 1/10 of a volt, which is quite significant. And here the cell overshoots the ambient voltage when in a self-recharge mode. A similar effect is described in the 4th phase of water. When the exclusion zone is penetrated with ultrasound, the exclusion zone goes down, and when the ultrasound is switched off, then the exclusion zone recovers but gets much bigger than before. Then it goes down again to the level it had before. This effect might also exist in the Reid cell, since changing voltages have an influence on the amplitude of the internally generated broadband signal, which I have shown earlier on. Yeah, this is an anomaly at 37 degrees Celsius, which is a fascinating issue. What you see up here, the purple line, is the temperature of the cell. Now here it is at 39 degrees Celsius, and we are lowering the temperature all the way down to 26 degrees Celsius. And here we are increasing the temperature again. So we have here the same shape, a clean shape. Now what we see here is that the voltage curve always follows exactly the temperature curve, because we have this temperature dependency. But for some reason, when we increase the temperature from 26 degrees up to 34 degrees, then the voltage does not follow this curve here. There is a cutoff at 34 degrees, and if you look at this curve carefully, the curve recovers again a little bit, and then this recovery ends exactly here. And then it's sort of, the curve just flattens out and gets flatter and flatter. And this second flattening out is exactly at 37 degrees Celsius. So the power output cuts off from 34 degrees Celsius onwards. The second cutoff is at 37 degrees Celsius. This anomaly shows that temperatures above 37 degrees Celsius make no sense, because above 37 degrees Celsius, the power generation efficiency decreases significantly. The best power temperature related performance of the cell is at 37 degrees Celsius. This anomaly might show that the quantum mechanical self-symmetrizing mechanism can be best circumvented at and below 37 degrees Celsius in relation with oscillating water. Yeah, I'm coming to the end. The applications of the Reid cell are in the low power area, like clocks, smoke detectors, household torch, camping lights, sidewalk lights, microsystems, digital gauges, sensors, toys, and whatever. Marketable products are in preparation by Markout Energy in Germany and Quantum Power in Seattle. My partner from Seattle, Mark Cuthbert, is here in the audience as well. Partners for research are welcome. What you see here on the picture are two cells. They are put in series to increase the voltage to 3 volt, because the LED needs about 2.5 volt to jumpstart. And here, whoever would like to have a more detailed explanation, I just wrote a book. It just came out last week. It's called Virtual Particles in Electromagnetism. Thank you for your attention.
Thank you very much. Thank you.